say, rapid team. I'll just begin with a very brief introduction. So I suppose we're on pretty good ground in terms of the introduction to the AMOC with the excellent introduction that we got from Susan a couple of weeks ago. I'll talk a little bit more about impacts, I guess, of the returning circulation. Just to kind of orientate ourselves to start with, this is a classic figure that gets shown pretty in rapid talks. This is the returning circulation viewed from 26 north in the North Atlantic, where the rapid array is. You have about 32 spherotrips of the Gulf Stream flowing northwards in the Straits of Florida. About half is recirculated in the equally warm waters of the subtropical gyre, the half of which continues up to the higher latitudes, where it loses buoyancy and sinks, forming North Atlantic deep water. Known primarily in the North Atlantic, deep western boundary current, which at the latitude of 26 north is really confined to the western boundary. So, kind of constructing this kind of ribbon for the last time, but it is a useful enough place to start, particularly from a rapid perspective, which takes an island view of returning circulation. I refer to the AMOC as the AMOC for this talk, but it does have a lot of other names, and if you were to look for the AMOC on Wikipedia, you wouldn't find an entry. So I think that's really kind of a little bit of a gap in our outreach activities, that you can only find a thermohaline circulation entry on Wikipedia, which is often the first place that people look when they're going to get into a subject. The importance of the AMOC, we know about the impact on climate. So this figure, the lower part of the slide, shows the deviations from the zonal temperatures. And the thing to see in this is the lovely warm temperatures that we get over northwestern Europe. And solely due to the ocean, there's also an orographic influence, which in the Himalayas act to steer the atmospheric circulation, giving predominantly southwesterly winds over northwestern Europe. And that does play a role also, but without a doubt, the heat released from the ocean, so it's particularly the heat released. So at about 26 north, you've got 1.8 petawatts. That's close to the maximum of heat transport. When you get up to the Greenland Scotland ridge, there's very little of that heat transport remaining, and that's really because it's been released to the atmosphere, and that's the element of the ocean in terms of heat release. Observations, not just the impact on climate, but the evidence of major changes in the past, and there's projections of a decline with climate change in the future. Looking back, this is a figure taken out from a summary by Wally Brooker. So this is a paleoceanographic slide. Now, I think it shows a percentage of depletion of delta O18. I always think about this as a temperature figure. So starting from today on the left-hand side, going in time, you see these large excursions from the top in the relatively warm Holocene to the ice ages. You can see that's a difference of about 20 degrees Celsius. This large fluctuations in the temperature led to people like Wally Brooker hypothesizing that the overturning circulation was really key to maintaining this relatively mild climate that we get in northwestern Europe, but in the northern hemisphere in general. And time you can see that there are some large excursions. This kind of large, kind of on and off scale type oscillations in the overturning circulation is kind of reminding of a driven oscillator. Now, there we go. Okay. And there are some indexity models that do show that AMOC is on and off state. Now, there's some very simple conceptual models that show that, particularly the Stommel box model is the classic one that where kind of all started from. But some immediate complexity models show an AMOC with an on and an off state, which would have a massive implication on climate. However, the IPCC, the Intergovernmental Panel for Climate Change, ranked this as a very likely, a less than 10% likelihood event. So it's an unlikely event, but with a high impact if something was to happen. What the IPCC predicts will happen is that the AMOC will slow down as we enter a high scenario going forward. In fact, in the low emission scenarios, which is shown in the top left-hand figure here, it describe an overturning that is decreasing. The high emission scenarios, which is shown on the right, show a more dramatic decrease. in the overturning circulation. And this is really pretty consistent throughout a range of the CMIP5 models. The IPCC rank it as very likely that the AMOC will weaken over the 21st century due to anthropogenic climate change. Now, that there may be some decades where increases due to large internal variability. That was the IPCC, but I don't think any of the coupled climate models actually captured the type of variability, particularly not the rate of decadal variability that we see in the rapid observations. These climate models really don't get that. This is just a very brief kind of outline of what I'm going to talk about. I'll spend the first part of this talk talking about how we measure the AMOC and why we're running at 26 North. The second one is the summary of the results, and this is a line, a decade of inevitable surprises. So that a report by Merritt Rojas and Harry Ryden came out in Science a couple of weeks ago, which revealed a lot of these results from the rapid array, and that was the title that they gave it, a decade of inevitable surprises. So measuring the overturning circulation. I'll start from a kind of a very generic point with a picture of the observations of the ocean. So the number of observations in the ocean through the decades going backwards in time. From about the 50s up to about the 1990s, really the only oceans of the ocean were hydrographic measurements, with the caveat that there was quite a bit of XPTs as well, which added to the density. Startlingly was an explosion in the amount of hydrographic profiles taken from the ocean, and that was really due to the Argo program. These you've got, I think, 4,000 at the moment, Argo floats in the global ocean, measuring temperature and salinity in the top 2 meters. And when you look at this final figure of the number of observations in the ocean, you say, well, surely we're already measuring all of the oceans. So one of the first questions would be, can something like Argo measure the overturning circulation? Background, we've got it's doing some dynamic topography. So the whiter contours indicate the regions of fast circulation. The predictor seeing there is the Gulf Stream. The black are the air profiles, and this is taken from May of this year, a typical distribution of the number of Argo floats in the North Atlantic. And to be honest, looking at that, you'd think you've got pretty good coverage. So what I've attempted to do is to measure the overturning circulation. You want to measure ocean circulation. You can make allotments in these regions of high dynamic topography gradients. And look at kind of a geographically true map like this isn't necessarily the best way to view that. If you can see, I'm not sure if it's very clear on this figure, but there's a black contour around the core of the Gulf Stream. Done in the next slide is to spread out, so to diffuse the gradient such that that black is spread over the whole of the Atlantic. And now, looking at the black dots, this is where the Argo floats would be if the gradient of mean dynamic topography was relatively constant over the whole of the North Atlantic. And see that the Argo floats don't really sample inside these regions of sharp dynamic topography. One of the reasons actually is that there's a number of Argo floats did stay inside North Stream closer to the Newfoundland region, where a lot of the rest of the western boundary really didn't hold any Argo floats. Argo doesn't measure in the sharp dynamic topography where we really need these measurements. The RAPID program is based on moored observations, and observations are a great amount of work. And you ask the question, how many measurements are you going to need to measure the overturning circulation? It's actually as difficult as you might first think. You might think you need a measurement every orographic correlation scale would be maybe 3 kilometers, maybe something like that. An Argo floats are deployed on a 3x3 box, so you might say 3 degrees of latitude. That would be an awful lot of mooring arrays. But in fact, when you start looking at the coherence of the circulation, currents are actually very meridianally coherent. And I'm focusing on a subtropical Atlantic now, and I don't know the answer to the question if you were to ask about the currents in the subpolar area. Provided by Joel Hershey. It shows a composite. So along the bottom in the blue line, we've got the measurements of the Florida current in the Florida Straits. And it's a positive composite, the composite of averaging on the left-hand side all of the surface velocities when Florida Strait is positive. On the right-hand side, all of the surface velocities when Florida Strait is negative. And really, the take-home message for this is that if you map 26 north where those Florida Straits measurements are made, you're capturing the variability over a large meridional extent. So you just need to choose a very good location to make your measurements. So north. A lot of the motivation for making a measurement of the overturning circulation came from the community. Certain climate models would define, oceanographic models would define the overturning circulation. So they sum up all the velocities, all the meridional velocities, and then they define a stream function. And going from a whole range of the Atlantic, a maximum of the overturning stream function is where the AMOC is defined in models. Traditionally around about 30 degrees north, those 26 degrees north to make our measurements. So this, first of all, are the Straits measurements dating back to 1982. So these are really crucial measurements that are made by NOAA in Miami. The high-quality transatlantic sections, with 5 in 2004 when the RAPID program began, and you're going to have 8 by early 16. Now, new before we started the program, actually, one of the really crucial elements of 26 North is that there's a sharp drop-off of the continental shelf near the escarpment. Now, this has 2 impacts. The first is that the western boundary cannot be approximated as a vertical wall, and very important for some of the assumptions that we make when we use astrophy and dynamic height differences to make our measurements. Secondly, is that this vertical wall or approximation to a vertical wall suppresses the mesoscale influence, and that was some work done by Thorsten Kanzow in the early years that really kind of validated these measures as a measure of a pretty meridional kind of overturning, only coherent overturning circulation. So to make our measurements at 26 north, and we'd of moored instrumentation to make these measurements. So this is the schematic of the array. So in the top plan of the array across 26 north, profile view going across with all of as we go across. So starting from Florida, you go across the Florida Straits. This is instrumented by the Florida cable, which makes those excellent measurements of the Florida current going back to 1982. From the Bahamas down to 77 west, so that's actually this really small little wedge that isn't in the grey in the middle figure. The current meter measurements, this is led by Bill Johns in the University of Miami. This is using direct current meter measurements, the northward flowing Antilles current and elements of the southward flowing deep west boundary current. This is the only part where we use direct current meter measurements. The rest of the array is a dynamic height array where we make measurements of temperature and salinity, construct density profiles, and take the dynamic height difference to calculate the transports across the section. All of this take a lot of work, and we've had a number of service cruises on a lot of vessels, including 3 UK vessels and a lot of US and I think German vessels over the lifetime of the project. For those of you who work with moored observations, this is what a mooring looks like. This is it being deployed over the aft deck of the US research vessels. Basically, large engineering constructions of we strap on to keep them vertical and instrumentation as we go down the water column to sample. I have an acoustic release, which I can hopefully this releases our instrument up to us. Go back to collect it. First of the size of this, our tallest mooring on the western flank of the Mid-Atlantic Ridge, which is 1,150 meters high, and in comparison with the Empire State Building or the Eiffel Tower, that's a long way down. A large part of measurements rely on the construction of density and dynamic height profiles. This slide, I think this is my favorite slide in the talk. It's the importance of millidegrees. we know from our microcap measurements, which are accuracies of salinity of 0.003 grams per kilogram in salinity, or give or take 3 parts per million, and an accuracy of 2 millidegrees. Now, I remember talking to, I think he was a climate modeler at a conference where he had just been expounding the inaccuracies of temperature in cold climate models. He was talking about SST, where there routinely are biases of kind of the order of 1 degree remaining in it. And he was asking me, why do you observationists always talk about, tenths of a degree change or millidegrees? And the reason is that they have a very, very important impact on transport. But a small bias of 0.003 in salinity in the east and the west of the basin in a measurement like RAPID results in a 0.7 surge of error in the AMOC estimation. Likewise, a bias of 2 millidegrees would result in a 0.6 surge of error. Actually, most of that is to do with temperature and salinity. But these very small different calibration can really impact the actual estimation of the returning circulation in a relatively large amount. What we're going to be adding to the RAPID measurements shortly is an error bar, so we'll be providing online, and that should be available shortly. One important thing actually is we provide annual error bars or annual accuracy measurements. And the thing about that is that we estimate not necessarily that the degrees of freedom reduce linearly. You have to take consideration of the deployment length and when these instrumentations were deployed. So actually make the AMOC calculation. So one that I hadn't mentioned previously was the Ekman transport. So this is the surface intensified, or the surface wind-driven transport. That's the left-hand figure here, the transport per unit depth figure. Green. It's fine to about the top 50 meters, and at 26 north is in the mean flowing northward, driven by the winds at this latitude. Going components, then in the blue line we have the stream in the Florida Straits. So this is fine to the top 700 meters and flows strongly northwards. Wedge, so that was the direct current meter measurements that I was talking about. That's in the blue line. So that's actually quite a small contribution in the mean, but has a very important contribution to the variability. The main part of the RAPID array, which is dynamic, essentially can be approximated by the dynamic height difference from the west to the east, and that's what's shown in the magenta on this left-hand figure. In 1,000 meters, we have southward flowing, so this is the southward gyre return flow. At this depth, we have got a small little bit of northward flowing Antarctic intermediate water and some southward flowing North Atlantic deep water. You can just about see two lobes of North Atlantic deep water and lower North Atlantic deep water. And we've got some Antarctic bottom water, but we don't actually measure that in a time variable sense. The AMOC from these, we sum together these components and integrate them vertically to create a transport stream function. To define AMOC, we take the maximum of this transport stream function, which is the stream function shown on the right-hand figure with the mean, and the red cross is the maximum of this overturning stream function. Is at about 1 meters depth and in around 17 or 18 surge. These elements together to generate a time series of these components, including the overturning circulation. At the Gulf Stream, this is a blue line, constant at about 32 surge-ups. We've got the Ekman component, which is the blue line, or sorry, green line, which is weak northwards. We've got mid-ocean transports, and I'll just take you back one slide. Ocean transport is this magenta line on the left-hand figure, just at the top 1,000 meters. It's defined as the mid-ocean transports down to the depth of the overturning circulation. So you have the Gulf Stream, the Ekman transport, and the upper mid-ocean transport, and that gives you the overturning circulation. For the first 10 years, so this is the full 10-year time series, the AMOC is 17 surge-ups, which is actually quite a bit lower than what we started off with. In the first couple of years, it was more like 18.5 surge, so we've seen a decline. The AMOC is important because it moves heat around the and the transport calculations are really led by Bill Johns in the University of Miami. Again, we've got this in various components. We've got the heat transport, or I suppose technically it's a temperature transport of the Florida current, that's in the blue line. The transport of the Ekman, which is in the green line. The mid-ocean, so this is the full mid-ocean now, not just the upper mid-ocean in the red line. The total, which is the sum of these, which is the black line. Now, between these two slides, you'll see that the black line on this slide and the red line on the slide before are very similar, and that's no coincidence. About 9% of the overturning of the heat transport in the overturning circulation. So, if you measure overturning circulation, you're really measuring the heat transport. At about 1.3 petawatts. I think this figure was 1.25. Going through a couple of the results. So Susan touched on this particular result, the first result in the last talk. When we started in 2004, there had only been 5 measurements of the overturning circulation from hydrographic sections. This is what's on here. It was reported Brighton, Longworth and Cunningham, which is a 30% decline in the overturning circulation since the 1950s. So with our first year of measurements, that the variability that we noticed over a period of a couple of weeks really encompassed what these 5 hydrographic sections had sampled. So I suppose the first result was that the overturning is not declining, it's noisy rather than stalling. For later on, because we're going to say something different at the end of the talk. We're able to determine was the seasonal cycle of the overturning circulation. So here we've got 4 favoured components. Again, we've got the overturning circulation in the red on the top left, the extreme, Ekman, and upper mid-ocean transport. The very large seasonal cycle, so it's 6 Virgips. It's got a peak in July. So I think when Thorsten Kanzel, who wrote the first paper on seasonal variability, the peak will have been in October. But in more recent times, the contribution of the Gulf Stream and the Ekman, both of which peak in July, has really led to the biggest peak in the overturning circulation seasonal cycle. That is the largest single component is the upper mid-ocean transport, and this is really driven from the eastern boundary, which was a bit of a surprise. You get a large seasonal cycle of 6 Virgips coming from, 4 Virgips coming from the upper mid-ocean, and this is why eastern boundary wind stress curl. There's been a number of updates to this recently. Orly Duché wrote an update in 2014. It was focused on a kind of a model perspective on the density variations. And just recently, I've been working with Lola Perez Hernandez, who has really kind of made the regional circulation around the Canary Basin with this kind of picture of the meridionally coherent overturning circulation. I'm not going to say much more about the seasonal cycle, but I'll move on to the interannual variability. And because this major downturn that occurred in the winter of 2009-10, we've got the in red, Ekman transport, and black, upper ocean, or the gyre recirculation, if you want to call it that, in the magenta line. First 5 years, the AMOC had bubbled along at a relatively consistent rate. And then in the start of 2009, it began to drop. Now, over 18 months, there was about a 30% weakening in the overturning circulation, as in here. There was a negative NAO in the winter of that year, and you can see that in the Ekman transport. So in the winter of 2009-10, there's a sharp drop in the Ekman transport. This, in fact, the main driver of it, the ocean transport had been strengthening southwards much earlier in 2009. So about the Gulf Stream flowing northwards, you've got a kind of a very constant Gulf Stream in the Florida Straits flowing northwards. That water either recirculated in the warm waters of the gyre southwards, or recirculated in the colder, deeper waters of the overturning circulation. So what we're showing is that more water was recirculated in the gyre rather than in the overturning circulation. It was affected majorly because, of course, if you return warm water with more warm water, you're not actually transporting a lot of heat northwards. Transport had implications for heat content. So there's several publications focused on the changes in the heat content in this subtropical gyre, following this large drop in the overturning circulation at 26 north. So up here just shows the region that we're considering, and the contour plot shows the heat content anomaly, or I think it's the area weighted temperature anomaly over this region during this time period. And see there's kind of not much going on up until about the start of 2010 in this, and you then see a sharp cooling over the subtropical gyre during this period. So it's kind of, it matches up that we see this drop in the overturning circulation, and we see this cooling further north of it. We were able to show in this paper by Cunningham et al. That it was the change in the overturning circulation, so the horizontal convergence, that was key rather than the amount of heat coming in from or being lost to the atmosphere. Not only did the overcirculation have implications for heat content, but it also had implications for sea level. So this paper by Goddard and Yen and co-authors that came out in Nature Communications in 2015 re-emphasized this. What you kind of figure here is literally the trended deseasonalized sea level composite for the northeast coast of the United States. Positive values indicate a sea level rise, and negative values indicate a sea level fall. And if you focus on the green bar there, just at the 2009 start of 2010, you can see it's a very sharp spike in sea level. In the city, this was a sea level jump of 13 centimeters, and these were able to relate this to a response to the amount drop. Right-hand figure, that's the kind of the mean and standard deviation, so you can see well outside of the range that had been sampled before. After the authors state that there's about a 13 to 17 millimeter rise in sea level per sphere drop in the AMOC. Now, I think it's a very important societal consequence for the kind of the densely populated sea of the United States. Pretty, you know, of rising global sea levels. On top of this, if you overlay a decrease in AMOC, you really are in a precarious sea level rise scenario. Our first big dip in 2009-10, those are the winter of 2007. The figure is just the deseasonalized overturning circulation. The dash indicates two standard deviations variability. So the winter of 2010-11, the overturning circulation. This was largely driven by the Ekman transports, which you mightn't necessarily immediately think is related to the ocean, but it was by Sarah Tawes and co-authors here. The ocean re-emergence, so the mechanism by which you get a very cold winter, you form deep cold mixed layers. This is capped over in the summer, and then these cold anomalies re-emerge the following winter when the mixed layers are formed, re-entrains these cold winter anomalies from the winter beforehand. That this re-emergence of sea surface temperature is linked to these two events. Doubles in the overturning circulation have occurred previously, including the winters of 69-70 and 78-79. These are all kind of coincident very cold winters in northwestern Europe. So the impact of the ocean on the atmosphere here is something that we're really beginning to understand, which takes us into the real kind of importance of why these measurements of the overturning circulation. The sea surface temperature anomaly pattern in the winter of 2010-11. Ian Buchan, who's a PhD student here, was able to show that this surface temperature pattern was strong enough to push the atmospheric circulation into a second NAO pattern. So this ocean-driven phenomenon of the re-emerging sea surface temperatures was strong enough to push the atmosphere into the second negative NAO. Not only that, but there's evidence that the correct initialization of these sea surface temperature anomalies led to successful prediction of the NAO. So that's a paper by Anna Maidens in the UK Met Office. That I think, you know, there's good to be made that if you're really interested in ocean dynamics and you want to understand that, then you should focus on content. But when you're interested in the impact of the ocean on the atmosphere, then the impact on SSTs, on the sea surface temperatures, really is what you want to consider. This has been submitted by Orly Duché. It links the fluctuations in the rapid transport to the observed sea surface temperature patterns. And she sees that AMOC leads North Atlantic sea surface temperatures by 5 months, and it's associated with this dipole pattern that you can see here, particularly cooler STs to the south and warmer SSTs over the subtropics. Cooler SSTs occurring in a region where you get large kind of hurricane formation. So the implications for forecasting, that you've got something that might predict these SSTs by 5 months in advance, really is a kind of a major element. Get to the long time period of results that we have so far, the decadal changes. These are figures updated from Speed et al. In 2014 to the whole 10-year time series. Over the 10-year time series, we have noticed a very sharp decline in the overturning circulation. We've noticed a decline of 0.6 of a spurger per year. Now, CC predicts that the AMOC slowdown should be of the order of half a spurger per decade. So we're seeing something that's much bigger than that. In this, the anomalies of the overturning circulation, Gulf Stream, upper mid-ocean and Ekman transports. We've got the trend lines and confidence intervals. You can see a decline in the AMOC, and this really only mirrored in the strengthening of the upper mid-ocean southwards. This pattern of a shift in the circulation from the overturning to a jerk circulation is something that's consistent over this 10-year time period. If we exclude the extreme negative event in 2009, this down is significant at the 90% level. This downturn is really large. It's much larger than we'd expect from a slow decrease of the overturning circulation due to anthropogenic forcing. So that kind of led us to ask the question, maybe it's part of a multi-decadal variability. Now, I think is a region that shows an awful lot of multi-decadal variability, particularly in sea surface temperatures and the Atlantic multi-decadal oscillation surface temperatures. So it's shown in the blue line here. So I'm only going to focus on the blue and the red in this particular figure. The blue shows the AMO sea surface temperature anomalies over the Atlantic since 1950s. We've got this large multi-decadal trend. The rest of rapid measurements towards the end, where we see a decrease in the overturning circulation, and there's evidence that there is a decrease, a slight cooling, or at least a decrease in warming of the sea surface temperatures over the North Atlantic. I mentioned earlier on in the talk that about a couple state-of-the-art coupled climate models. Figure from Robertson Jackson that came out last year, I think, is that the trend that we see in observations is actually much larger than any 10-year. Well, this was done on 8-year trends. It's larger than any 8-year trends that are present in a range of coupled climate models. The implication really is that these models do not capture the magnitude of decadal variability that exists in the ocean. If we think about kind of variability that's going on at the moment, including the so-called hiatus in global warming, you see this is the pattern of temperature anomalies in 2014. So the 2014 was one of the hottest years on record in an awful lot of places. But there's a big cold spot over the North Atlantic, which is consistent with the decline in overturning circulation that we're seeing at 20 north. For the final bit of the talk, look forward by looking backwards. The question is, can we reconstruct ocean circulation in the past? And to do this, we've done some analysis of tide gauge records along the US East Coast of a long time series, which is something that direct observations of ocean circulation. There really doesn't exist really long series. So these tide gauges offer basic properties of the water column back to a long time period. Now, this is kind of a classic problem in oceanography. A classic way of doing it would be to take a gauge on Miami Beach and a tide gauge in the Bahamas and look at the variations between them, and you say we've got an estimate of the flow current. We've taken a different approach. We focus on the gradient along the US East Coast. From this figure modified from Yin et al. In Nature Geoscience. And this shows the mean dynamic sea level. So you've got the large That's what the water around the subtropical gyres, and then the dip of the waters in the subpolar gyres. Now, to a reduced AMOC, this gradient really does change quite substantially. It causes us to look at the change in the gradient north and south of Cape Hatteras. So that's the difference between the subpolar gyre really is what we're doing there. Gauge data really do naturally kind of break into groups along this coastline, sort of Cape Hatteras and north of Cape Hatteras. Cape Hatteras being where the Gulf Stream leaves the coast. So you've got this composite, which is what's shown in the line on the bottom right of this figure. So you've got the sites which are sites 1 to 6 on the map on the left-hand side, and sites 7 to 30, which is the top line on the bottom right figure. That's site 7 to 30, and you see this kind of breaking correlation between the tide gauges on either side of it. Estimate of the circulation, we take the difference between the south minus the north, and that's the center line on this right-hand figure. This is our index of circulation that we think is the best using these tide gauges. One kind of big advantage that we have using gradient along the coast is that it's unaffected by mesoscale eddies. Now, you remember back to the start of the talk, there was a figure of Joel Hershey who had shown that the on the western boundary is very meridionally coherent. So we know that we're getting something that's measuring the transport of a large area as we're not being affected by mesoscale eddies. To give it a feel for this circulation index, it really gives an index of the circulation intergyre region between the subtropical and the subpolar subgyres. Projectable index onto satellite surface velocities, which is what we've done in this figure here. A positive is associated with a more northerly path of the Gulf Stream. Quite interesting problem to think through in terms of relating things like the Gulf Stream as a purely western boundary current, even overturning circulation, and then an index such as the Gulf Stream North Wall, and how all of these fit together is very interesting research problem, I would say. With a more northerly path of the Gulf Stream, but it's also associated with more northward transport in the subpolar gyre and more southward transport in the tropical gyre. Now, of course, these are the best we can do with observations, but we were able to validate all of these in a high resolution ocean model. And in fact, the sea level gradient index of the heat transport at 40 degrees north, which is closely related to the overturning circulation. We can relate this heat transport changes to the heat content changes north of this latitude. That's what we're showing here. We've got our sea level index in the blue line. We relate it forward in time, so you transport in time to give you a heat content estimate. And that relates very closely to the black line, which is the temperature, the weighted temperature anomaly in the top 500 meters from 40 to 60 north. The line in this figure is the accumulated NAO, so it really looks like the NAO is what's forcing these major changes in the sea level gradient and consequently in the circulation of the North Atlantic. For why our sea level index leads the changes in the heat content, we look at the evolution of the heat content through time. So large warming coming up through the mid-90s, and you can see there was an accumulation of heat, positive content anomalies along this intergyre region. So I'm looking at the center figure now. So this is from 1985 to 1994. From 1995 to 2004, that heat content really transported up into the subpolar gyre, warming the waters there and eventually warming the sea surface temperatures. So we're able to relate this sea level index back in time, back to the 1920s. Relate these three factors together. We've got the AO again in the red dashed line. This is accumulated forward in time. We've got our sea level index, which is the blue line, and got the AMO, which is the black line. So the multidecadal variations of surface temperatures. There's a bit of blip in the 1940s, and sea surface temperatures in the 1940s are very cool kind of thing. Anyway, but there's some certainly about 1950 onwards you get very good agreement between. So that we've provided some evidence that ocean circulation is really what is responsible for the multi-decadal variability in the North Atlantic. This is a reconstruction, of course, and direct observations of the ocean circulation, such as rapid. I would say, the next major question that we've got is: will rapid confirm the same kind of the same mechanistic link between the overturning circulation and the AMO? So interestingly, the tide gauge reconstruction needed the difference between the subtropical and subpolar. So maybe we'll need an OSNAP and a rapid, or some subpolar measurement of circulation combined with the rapid measurements to really understand these changes that are important for these multi-decadal variations. And I think the important implications of the AMO is that we sustained direct observations to confirm this link. So I'll finish up with a bit of kind of a chat sustained observations. Sustained observations is something that I'm very, very passionate about. And I like to motivate it in this way. So the figure on the top left is a figure from Charles Keeling in 1960. He had just made 2 years of measurements of CO2 at the top of Mauna Loa in Hawaii. And he wrote a paper and he was describing things much like we've been describing here in this talk about seasonal cycles and short timescale variability. If we fast forward to the present day, we've got the same data extended over the 50-year lines at this stage, and in curve. As time has gone on, what the Keeling curve has really shown is the most famous record of the continual rise of anthropogenic CO2 in the atmosphere. So in 50 years' time, I wonder will we say that the rapid measurements have shown us something similar, and has documented the impact over a period on a declining overturning circulation. Phrase particularly from a paper by Wunsch, Schmidt and Baker in the Proceedings of the National Academy of Science a couple of years ago. Understanding of climate change is a problem for multiple generations. One generation of scientists has to make provisions for the needs of successive generations rather than focusing solely on its own immediate scientific productivity. Today, will likely prove of little interest in 100 years, but adequate samples, carefully calibrated, quality controlled, and accurate data for key elements of the climate system will be used indefinitely. To show that isn't just a kind of a rallying call to get lots of us to go out and make measurements, it is very, very true. Showing again here this figure that we published in our paper 2 weeks ago, or a couple of 2 weeks ago in Nature, and this used data right back from the 1920s. I went through the old NOAA archives for some old figures of people who had done this, who had gone out and made carefully calibrated, accurate measurements and carefully archived measurements of tides. So there's this handsome young man in a nice hat and tie in Boston in 1926. We used his data. There were the Mung Ho lads in 1931 in Kettle Bay installing a tide gauge using a sledgehammer. Things had moved on a little bit in 1974. I think the sledgehammer was gone at least. South Carolina, they're installing tide gauge, and data that they made, that they so painstakingly and so accurately made, have been used in cutting edge science right up to the present day. We hope with rapid, we hope that these measurements that we make will provide a long-term record of very important and essential climate variable. And going forward, we hope that. So this is a picture of the original team. I don't think it was 2004. I think it might have been 2006. This was taken in. You have people like Harry Bryden, Joachim Moratsky, who drove a lot of the kind of, I suppose, the theory and the kind of how exactly we should measure the overturning circulation. To begin with, you have people like George Cunningham, Bill Johns, modern Chris Minan, who remake these measurements or measurements for a long time. I think, into other places, but Bill Johns and Molly Barron are still making the measurements. Next, we've got Darren Rayner. He's one of the few people here in Southampton who's still working on the project. I should say Mercer is in this picture too, who's sitting next to me here. And Rayner is one of the few people who's still going to cease to make the measurements in Southampton. Southampton. This is a picture from the last cruise in 2014. Got Ainers there again. We've got some of our technical crew. We've got Steve Whittle, Dave Childs, Chris Crowe, and Colin Hutton. Together, they've spent an awful lot of time at sea. I think they've spent over a year at sea each. I think some period of time at sea making these measurements rapid. But I have no doubt that all their labours were certainly not in vain and will prove major use for us at the present and going forward for future generations of scientists also. So I'll leave it there and I'll take any questions that people have.
I'm sure everyone's clapping at their desk. Big carrot. So Sarah, I'm going to have to rely on you to see who wants to ask questions. I can't see the screen, but if there's anyone raising a virtual hand or just wants to chime in with a question for Gerard.
Yeah, so far there aren't any in the chat. Yeah, there's also a little, I don't know, hand, I think to the right of your name that you can sort of raise if you ask something.
We've got a question here in Southampton from Eric Straukas.
AMO. What is the change in the MO? So you've got it's based on sea surface temperature. What's the corresponding change over a sort of 50 to 80-year cycle in the overturning circulation in terms of Sverdrups? Because that's based on models, as I understand it, because we don't have measurements for that period. Do you know what the you can see in the SST, that means